Hello. In the last lecture, we talked about how to find out the natural frequency mode shapes. We talked about the orthogonality of the mode shapes and what is the expression of orthogonality in terms of modal matrix. We also talked about how to mass normalize a mode shape and what is the benefit of mass normalization of a mode shape. So, in this lecture, we will talk a bit more about orthogonality of mode shapes and then move on to finding out the free vibration response of a 2 degree of freedom system through a numerical example. So, let us get back to orthogonality of mode shape. So, in the last lecture, we had said that phi, which is the modal matrix, which is n cross n for a n degree of MDOF system, into the mass matrix transpose of this, which is n cross n, into phi, which is again n cross n, is going to be a diagonal term with all 0 of diagonal terms. And then we have also said that if we mass normalize the modal matrix, if this is mass normalized and then obtain this product, then we will have a same diagonal matrix, but now the diagonal terms are going to be unity, or we will get an n cross n identity matrix, right. So, what we are going to do today is to prove the orthogonality of the mode shapes. We are going to prove that for any linear vibratory system, the mode shapes are always going to be orthogonal to each other, or this expression is going to hold. So, let us move into the derivation. So, let us start with the equation of motion. So, this is a generic MDOF system with n degrees of freedom. Now, we know that under pth normal mode of vibration, my u ut is going to be Cp, which is a constant, Rp into cos omega p t minus phi. Okay. So, this we have derived, and this is the pth normal mode of vibration of the system. So, since this is a normal mode of vibration of the above system, this should be a solution of this system. So, what we do is that I substitute this solution into this equation. So, therefore, I am going to get minus omega p square into C p into m into R p into cos omega p t minus phi plus Cp into K into R P into cos omega p t. So, we can always cancel out Cp. Now, Rp, needless to say, it is the pth mode shape. And omega p is the pth natural frequency. Okay. So, this is the equation that we have. So, cos omega t p minus phi p is the phase angle. Please do not confuse it with the modal matrix vector that we are talking about. So, this is an entire, this is just a angle which is denoting the phase angle. So, cos omega p t is cannot be equal to 0 for all t. Therefore, we can write omega p square into m into R p is going to be k into R p. Okay. So, now what I do is pre-multiply both sides So, I take the transpose of the qth mode shape and pre-multiply both sides of the above equation with RQ transpose. So, RQ transpose is the qth mode shape. Okay. So, if I do so, I get this equation as omega p square R q transpose into m into R p is equal to R q transpose into k into R p. So, let me call this as equation 1. So, we have to keep this equation 1 in mind. Now, let us start doing the same exercise, but this time we consider the qth normal mode of vibration. Okay, and say that ut is nothing but CQ RQ cos omega q t minus phi q, where needless to say that RQ is the qth mode shape, omega q is the qth natural frequency, and this is the phase angle. Okay. So, now if we substitute this into the equation of motion, I am going to get this as minus omega q square into C q m into R q into cos plus again we CQ can always be made to 0 where CQ is constant. So, I forgot mentioning this, that this is a constant. Okay. So, I can always cancel out CQ, and then I can use the same logic that cos omega qt minus phi q cannot be equal to 0 for all t. Therefore, I have minus omega q square into m into r q plus k into r q is equal to 0, which can of course be written as omega q square m into r q is equal to k into r q. Okay. Now, what I do is that I pre-multiply both sides of this equation by the transpose of the pth mode shape. Sorry, I pre-multiply by the transpose of the pth mode shape, and if I do so, I am going to get omega q square r p transpose into m into r q, that is equal to r p transpose into k into r q. This, let me call this as equation 2. Now, if I take transpose on both sides of equation 2, what am I going to get? I am going to get omega q square r q transpose m transpose into r p is going to be r q transpose into k transpose into r p. So, let me call this as equation 3. Now, let us carefully look into this equation. M and k are symmetric matrices. Therefore, M transpose is equal to M and K transpose is equal to K. Therefore, in equation 3, I can rewrite it as right. I can just, in place of M transpose, I can write this as M. In place of K transpose, I can write this as K. So, this is equation 3. If we remember our equation 1 was, if I rewrite the equation 1 was omega p square r q transpose into M into r p was equal to r q transpose into k into r p. This was my equation 1. Now, we see that equation 1 and 3 are almost similar, except that it is one is multiplied by omega q square and one is multiplied by omega p square. Now, this is interesting. So, let us see what we can do with this. So, what I am going to do is I am going to subtract equation 3 from equation 1. So, I am going to subtract equation 3 from equation 1. If I do that, I will have omega p square minus omega q square into r q transpose into m into r p transpose, sorry, not transpose, into r p, and that is going to be equal to 0, because the right hand side of both equation 1 and equation 3 are same. Okay. So, from this equation we can say that either omega p square minus omega q square has to be 0 or this expression has to be 0. Since p is not equal to k, omega p square is not equal to omega q square. Okay. Since my p is not equal to q. So, this part of the equation is not equal to 0. So, therefore, from this expression we can say that r q transpose into m into r p transpose is equal to 0, and this is the expression for orthogonality of mode shape for p not equal to q. So, this is the equation for orthogonality of mode shape. So, therefore, we have proved that if we take any generic system, any arbitrary system, the mode shapes are going to be orthogonal to each other, because the mass matrix and the stiffness matrix are symmetric. Again, I have said earlier that mass and stiffness matrix are going to be same for any linear vibratory system. Now, let us see what we can do further from this. So, this holds for this equation has been written for any arbitrary p and q. So, I can write this for any p and q, p being from 1 to n, q being from 1 to n. So, if I do that, I can actually write that in a matrix form as phi transpose m into phi is going to be a diagonal term, diagonal matrix, okay, where phi is the modal matrix or the matrix whose columns are the mode shapes arranged in order from 1 to n, and M is of course the mass matrix. This is going to be a diagonal matrix if phi is not mass normalized. If phi is mass normalized, then this expression is going to be equal to an identity matrix. Okay. So, this is mass normalized modal matrix. What is mass normalized? Okay. So, now there is a corollary to this expression. So, we have seen that R q transpose M R p is going to be 0 for all p not equals to q. Now, if this is equal to 0, if we go back to our equation 1 or equation 3, then the left hand side of the equation is going to be 0. Therefore, the right hand side of the equation is also equal to 0. So, we can a direct derivative of this expression is that R q transpose into the stiffness matrix K into R q Rp into Rp is also equals to 0 when P is not equal to K. Right. So, from equation 1 we can also derive this. So, this is also an alternate expression for orthogonality of mode shapes, where we say that the mode shapes are also orthogonal with respect to the K matrix. Now, let us look what we can do about this expression if it is to be written in terms of modal matrices. So, if I write it in terms of modal matrices, this expression that R q transpose K R P is equal to 0 for all P not equals to Q can be written in matrix form as phi transpose K into phi is equal to 0, where phi where phi is equals to a diagonal matrix whose off diagonal terms are equal to 0, where phi again is the modal matrix. Okay. So, if we do write out the same equation with the mass normalized modal matrix, then this is going to be a diagonal matrix with the diagonal term being the square of the natural frequency. This is an interesting exercise to do and see whether we are going to get this expression. So, if phi n transpose is the mass normalized modal matrix. Is going to be a diagonal matrix whose diagonal terms are nothing but the square of the corresponding natural frequencies. So, with this we are going to move on to our next slide, which talks about. So, all this time we have been finding out the natural frequencies and the mode shapes from the equation of motion using normal mode of vibration, using the definition of normal mode of vibration. So, now with all the examples done, we are in a position to find out the natural frequencies and mode shapes of the system. We know the orthogonality conditions of the mode shapes, we know how to mass normalize the mode shapes, and what would be the expression of orthogonality when we have mass normalized mode shape. Now, let us see whether we can derive this natural frequency and mode shape as eigenvalue problem and obtain them numerically. So, let me first find out the expression for, let me first find out the expression for the, so the initial equation of motion is m u double dot into k into u is equal to 0. So, we know that this can actually be written as m into, this can actually be written as m into minus omega square a 1 A2 plus k into A1 A2 equals to 0. So, this further can be written as k into A1 A2 omega square m right. So, this can be written as m inverse k into A1 A2 is equal to omega square into A1 A2. Okay. So, this you can realize is an eigenvalue problem for the matrix M inverse K. So, for this matrix M inverse K, omega square are nothing but the eigenvalue of this matrix M inverse K, and A1 and A2, that is the mode shape, is the eigenvector of this matrix M inverse K. So, for a large problem where the number of degrees of freedom is large, using the previous analytical method to find out the natural frequencies and mode shape can be bit tedious, and it can be therefore obtained numerically by obtaining this matrix M inverse K, and the natural frequencies and mode square of the natural frequencies and mode shapes are going to be the eigenvalues of this matrix M inverse K. There are several numerical algorithms available to efficiently find out the eigenvalues and eigenvector of a large system, and any of those numerical algorithms can be adopted if we want to find out mathematically or through programming the natural frequencies and mode shapes of a multi-degree of freedom system with reasonably large number of degrees of freedom. With this, we will end this lecture. Thank you.